Hello, everyone. Today, the Embry Riddle Aeronautical University Sol Invicta team will be presenting on the Ohio State University District. The team at Sol Invicta is made up of 5 skillful workers. My name is Geraldine, and I am the project manager. Sean, Chase, Ian, and Michael will also be presenting, and our advisors, Dr. Rodriguez and Ms. Persking, are joining in the audience. The name Sol Invicta is no coincidence and was formulated based on core values. We pride ourselves in innovative designs, negotiable agreements, versatile products, incomparable service, customer-focused products, timely updates, and ardent workers. The Ohio State University is a 1,665 acreage university in Columbus, Ohio, and is the largest in the state. If you take a look at the Global Horizontal Irradiance, or GHI map, you can see that Columbus, Ohio has a relatively low global horizontal irradiance of 3.94 kilowatt hours per meter squared per day, opposed to here in Daytona Beach, where it is 5.09 kilowatt hours per meter squared per day. GHI is a measure of how much energy from the sun we can use. So we took this information into consideration along with OSU's sustainability goals, which is embodied by the Ohio State's President's Climate Leadership Commitment to formulate our customer-focused design. Here we have an aerial view of the assigned medical campus, which is bounded by the red line. Our agrivoltaic design is located at the Waterman Agriculture and Natural Resources Laboratory Complex, also bounded by the red line. Before we could begin designing, the team was faced with a significant amount of missing data for Harding Hospital and Davis Heart and Lung Research Institute. We brainstormed and decided to find correlations between known data of weeks of similar temperatures. The problem was then solved by using multiple linear regression, which produced unique equations and yielded approximations of missing data. I'll now pass it on to Chase with the equipment selection.
Hi there. So solar panels with phosphorus-dipped N-type cells were selected because they do not negatively react with oxygen like the boron-dipped P-type cells that are normally used in space. Also, the IBC N-type cells do not have light-induced degradation caused by the sun. SunPower's Maxion 3 solar panels were chosen based on its superior power, efficiency, cost, and degradation. The 10,000 volt amp SolarEdge inverter with HG-Wave technology was chosen based on its superior efficiency and the number of PV panels that are able to be wired to it. Additionally, it was chosen because it is a smart inverter, which allows Ohio State University to monitor the PV panels, inverters, and batteries from SolarEdge's app on their phone or computer. If a piece of equipment is malfunctioning or damaged, it is easily identifiable, lowering the time and cost of maintenance. Normally, if a PV panel is shaded or damaged, the other panels within the same string can only produce the same amount of power as the weakest link. Paired with SolarEdge's P485 optimizers, our systems allow each panel within a string to produce the maximum amount of power it can, greatly improving the efficiency. With only 2 batteries available that work with SolarEdge inverters, the SolarEdge Energy Bank was chosen since it was specifically designed to work efficiently with these inverters. In addition to being able to monitor battery performance from the SolarEdge app, there's also a feature called WeatherGuard, which sends alerts if a large storm is detected by the National Weather Service and preemptively charges the batteries through the grid to full capacity in case there's an outage in the distribution grid. Now passing it off to Sean for conceptual design.
Thank you, Chase. The Ohio State Medical District photovoltaic system consists of 7 rooftop and 3 parking garage systems. These systems total 3,996 panels, generating 1.6 megawatts. The rooftop systems utilize roof penetrating mounts, and the garages utilize carport mounts. Panels across the medical district are fixed flat or 0 degrees. And the batteries for the resiliency challenge total 432 units. The average GHI value of the district is 1,340 kilowatt hours per meter squared per year. The 9th Avenue garages contain 1,548 panels, generating 619.2 kilowatts, and consist of the chosen carport mounts. These buildings provide power to charge over half of the batteries for the resiliency challenge at 240 units. Mealing Hall contains 126 roof penetrating panels generating 50.4 kilowatts and charges 21 units for the resiliency challenge. This system has less panels than it has space for in order to reduce system cost as its load profile is low. Ross Hart Hospital has 504 panels supplying 201.6 kilowatts to its own meter. Atwell Hall and the Safe Auto Garage generate a total of 237.6 kilowatts, supplying to 99 units for the resiliency challenge. Harding Hospital generates 93.6 kilowatts to 18 units to itself for the resiliency challenge, and the Davis Heart and Lung Research Institute generates 64.8 kilowatts. McCampbell Hall and Dodd Hall generate 324 kilowatts, and McCampbell Hall charges 54 units for the resiliency challenge. Our agrivoltaic system consists of 2,120 panels generating 848 kilowatts of power. All panels in this system are fixed at 40 degrees, matching the location latitude to maximize generation from the sun. The ground-mounted system will be tall enough for livestock to graze under and farm equipment to get by. Our team's system expected operation, using Harding Hospital as an example, will be focused on peak shaving. The building's load profile is large, so the solar panels and batteries will be working together in the peak shaving strategy. The red line in this image above the gray load profile shows the resiliency challenge charge of battery relative to its full capacity, showcasing its use in peak shaving. Back to you, Chase.
Thank you, Sean. This heat map, which is provided by the Solar District Cup organizers, displays the generated power of 1,400 kilovolt amps from our agrivoltaic system could potentially cause issues in the distribution grid. The inverters ensure that the phase angle of the produced AC power matches the grid. So in this case, a kilovolt amp is roughly equivalent to a kilowatt. Since the proposed agrivoltaic system is only 848 kilowatts, this means that the grid should have no issues when the system is interconnected. The main issue, however, to consider is voltage drop due to the large distance between agrivoltaic system and the interconnection point at Carmack Road. This distance is 1,380 feet and is shown by the yellow line. To prevent blackouts or potential voltage and frequency abnormalities in the grid, wire gauges were calculated to only allow a maximum of a 2% voltage drop for all PV systems in this proposal. Additionally, wire gauges were selected on the notion that each inverter is wired separately. This is to maintain a lower current to ensure a low voltage drop from 240 volts. If the proper wire gauges are implemented, there should be no negative impact from the agrivoltaic system on the distribution grid. Concerning the PV systems at Ohio State University's medical campus, the heat map displays that the distribution grid should only be delivered a maximum of 3,300 kilovolt amps. The only PV systems that pose a threat to the distribution grid are the ones delivering power to the Comprehensive Cancer Center and Wexner Medical Center. However, due to their very large power consumptions, it is highly unlikely that any of this power will ever be sent into the grid. There are two different wiring schematics in this proposal. This is the schematic used for PV systems without batteries. Among these systems are the agrivoltaic systems, along with the PV systems located on Davis Research Institute, Dodd Hall, and Ross Hart Hospital. Note that there are 6 panels per string and 3 strings per inverter. Also, the system connects directly to the building meter after the inverter in the schematic. In contrast, the PV systems with batteries will incorporate the SolarEdge backup interface. This is to ensure that the connection to the grid is severed before delivering power from the batteries to the buildings during an outage. This is to maintain compliance with UL 1741, which states that the grid-tied inverters must monitor the distribution grid and disconnect if there is a power outage or abnormalities in the grid's voltage frequency. With the exception of Harding Hospital, each PV system with batteries will deliver power to either the Comprehensive Cancer Center or Wexner Medical Center. This is to ensure the systems supplying Harding Hospital as well as these 2 buildings meet the resiliency challenge, even after power loss from voltage drop. As long as the proper wire gauges for each system is implemented, the proposed PV systems will pose no threat of causing issues to the distribution grid. However, a power loss of up to 2% is expected across the board since wire gauges were selected based on a maximum of a 2% voltage drop. Although this is unfortunate, it secures the safety of the distribution network while ensuring that the cost of wire is not overwhelming. And now here's Ian with project financial analysis.
Thank you, Chase. An NREL report from 2018 stated that the average cost per watt for a system of our size is $1.71. The reports divides the cost in specific sections like the average cost of inverters, wiring, construction, among others. The team noticed that our costs were different than the average cost in the report, so we decided to replace the cost of the inverter and the mounting cost with our own. Our final cost per watt was $1.43 for rooftop and ground mounting systems and $1.41 for carport systems. Using these inputs, the team calculated a PPA price of $0.148 per kilowatt hour, a project IRR of 10%, a payback period of 9 years, and a project net present value of a little over $2 million. I'll now pass it to Michael with the development plan.
Thank you, Ian. The development plan is comprised of several tasks. One task is identified in the zoning ordinance for our given district. As you can see on the right, the OSU Medical Campus and the Waterman Agriculture and Natural Resources Complex are both identified as research parks. Another task is researching and identifying the several codes that will be applied and adhered by our proposed system. Presented on the left is the federal level in the form of the International Code Council, as Ohio is one of the states in the country that is a member of the ICC. The permits and codes within the state of Ohio are presented at the center, and the permits and codes within the city of Columbus are presented on the right. Another task is adhering to the 2017 Master Plan of OSU and ensuring our proposed system would not conflict. The buildings highlighted in red are buildings OSU planned to implement either demolitions or renovations, but because of the date of the master plan, it would not obstruct the future implementation of our system. Lastly, another task is identifying any potential risks that may affect the proposed system. A major risk identified would be the amount of snowfall that has historically affected Ohio. The graph presented shows data of snowfall of the state, with the winter months being the heaviest. The team is passionate about solar and brainstormed various ideas to have our proposed system to engage with OSU. One idea is to implement solar skins on chosen panels in the proposed system, as presented on the upper right with Brutus Buckeye on the top of Dodd Hall, and the lower right, with the Ohio State University logo on top of Ross Hart Hospital. Another idea is to implement EV chargers throughout the campus, though limited within the parking garages. Now bring it home, Geraldine.
I got it, team. Displayed here are 7 distinct OSU sustainability goals found under the resource stewardship category. The team decided to focus on 3 of these goals and formulated an RAD approach where we would reduce building energy due to our panel shading on roofs. We will work towards achieving carbon neutrality by implementing our agrivoltaic design, which preserves trees and waterways, and help to develop university-wide standards with the implementation of EV and multi-purpose charging stations. Sol Invicta is a determined team prepared to do the work to make a positive impact for a greener and cleaner world for all. Our competitive design highlights the medical campus with 3,996 panels and 1.6 megawatts of power, and an innovative agrivoltaic field with 2,120 panels and 848 kilowatts of power. Our reliable and dependable batteries have specs of 5 kilowatts per 9.7 kilowatt hour and 432 units. Our system will financially benefit OSU with a stellar project IRR of 10% and an impressive payback period of 9 years, with a project NPV of just over $2 million. Finally, to showcase the school spirit and provide sustainable products for OSU's 61,000 students, Sol Invicta's customer-focused design includes OSU-branded solar skins, multi-purpose solar chairs, and EV charging stations, which distinguishes us from other solar companies. Thank you for listening. We'll now take this time to engage in any lingering questions.